This is the second half of section 6.1. We want to talk about orthogonal complements. So if we have a subspace, say W, maybe envision it as that plane in Rn, then the orthogonal complement of W is the set of all vectors that are orthogonal to W. And so that means the set of all vectors that dot to 0 with any vector in W. So here's the actual mathematical definition. W perp, that's how it's pronounced, W perp is the set of all x in Rn such that x dot W is 0 for all W in W. And so you need to know that definition. And we have a proposition here that tells us that two things. W perp is a subspace, and that's a homework problem in my math lab. And the second part of the proposition says, if W is spanned by a set of vectors, let's say V1 and V2, then to see if a vector is in W perp, you don't have to dot that vector with every vector in W, which is infinitely many vectors. You only have to dot it with the two vectors that span W to see if that's 0. So x is in W perp if and only if x dots to 0 with the vectors that span W. So let's see how we can put that proposition into work. If W is the span of this vector, so that will be a line in R3, describe W perp. All right, so by number 2 in that proposition, W perp is going to be the set of all vectors, and I'm going to use linear format so I'm not taking up so much real estate. Set of vectors A, B, C in R3 such that ABC dots to 0 with the vector that spans W. So A, B, C dot the single vector that spans W, 6, negative 2, 3, is 0. Okay, and we can clean that up a little bit. That's just the set of all vectors, A, B, C. I won't bother saying in R3 because it's obvious they're in R3 because they're 3 coordinates. So the set of vectors A, B, C such that 6A, so I'm going to do the dotting over here, minus 2B plus 3C is 0. So it's the set of vectors that satisfy that one equation. That's a plane in R3. All right, so that's a plane. And every vector in that plane is orthogonal to this vector here. Every vector in that plane is orthogonal to 6, negative 2, 3. Okay, let's do an example that we can't really visualize because it's in R4. So suppose W is the span of two vectors, V1 and V2. Find a basis for W and a basis for W perp. There's nothing to do in terms of finding a basis for W. A basis for W is just V1, V2. And the reason is that a basis has to have two properties. One, it needs to span the space. Now the spanning is automatic by the definition. W is spanned by V1 and V2. And then the other part of a basis is that you have to be linearly independent. Well, V1 and V2 are linearly independent because V1 is not a multiple of V2. So the only work we have to do is to find a basis of W perp. So W is spanned by two vectors. By the proposition above, we only need to find vectors x such that x dot v1 is 0 and x dot v2 is 0. So let's write that out as equations. So x dot v1, if x is x1, x2, x3, x4, x dot v1 is x1 minus x3 minus x4. So I'm just doing that in my head. And that should be 0. And then x dot v2 is x2 minus x3 plus x4. And that should be 0. So we're solving a linear system of two equations in 4 unknowns. That's all we're doing. So this is going to be if and only if. Let's write this in matrix form. 1, 0, negative 1, negative 1, 0, 1, negative 1, 1. If that matrix, which I'll call A, times x1, x2, x3, x4 is 0, 0. So that's the matrix form of that linear system. And so what we want to do is we want a basis for null A. Because we're solving AX equals 0, we want all the solutions, so we want a basis for null A. So what we do is take A, augmented with 0, and we reduce it. But we'll see it's already reduced. So 1, 0, negative 1, negative 1, 0, 1, negative 1, 1, augment with 0, 0. It's already in reduced echelon form, so we can just go ahead and write down what the solution is. Let's start at the bottom with x4. That's a free variable, so we'll call that t. x3 is also free, call it s. x2 is s minus t, and x1 is s plus t. So our basis will consist of the s vector and the t vector. So a basis for w perp is, all right, our s vector 1, 1, 1, 0, and our t vector 1, negative 1, 0, 1. All right. So it's not bad once you know how to do it. Here's the big theorem for today. It took us a while to get here. Recall, if A is an m by n matrix, you can think of A as a linear transformation from Rn to Rm. And we had four vector spaces that were of interest: row A, col A, null A, and null A perp. And so let me show you, well, let me remind you of where these vector spaces live. Null A lives over here, as does row A. Col A lives over in Rm, as does null A perp. Sorry, null A transpose. Null A transpose. All right, so what this theorem says is that we know that null A and row A live over here in Rn, but they live there in a very special way. They're completely orthogonal. So row A perp is null A, meaning the only vector they have in common is the 0 vector. Same thing over here, col A and null A transpose live in Rm in a very special way. They're orthogonal subspaces. So we can picture that with an actual example here. A is a 2 by 3 matrix. I've already reduced A. A maps R3 to R2. So row A and null A are subspaces in the domain, which is R3. Okay, let's find a basis for null A. We want to reduce the augmented matrix. So for a basis for null A, we can just find use the reduced matrix and augment with 0. So here's our reduced matrix B. This would be our B. B augmented with 0. If we find a, so I'll just go a little slower. B augmented with 0 is the matrix 1, 0, negative 1, 0, 0, 0, 0, 0. So x3 is free. x2 is also free, I'll call that S, and x1 is T. So a basis for null A is going to have two vectors in it, one vector for T, 1, 0, 1, and one vector for S, 0, 1, 0. So two vectors in R3, and if those two vectors are linearly independent, they're going to span a plane in R3. So imagine that this green plane is null A. Okay, find a basis for row A. So at the end of the last video, I showed you a little box as a review of how to find a basis for row A and col A. A basis for row A is going to consist of the non-zero rows of B. So in this case, it's only one row, 1, 0, -1. I'll write that vector as a row. So geometrically, row A is a line in R3 because it's a space spanned by a single vector, and you can imagine it as, or envision it as, this red line here. This is row A, and I've drawn them to be perpendicular, and in fact they are, because if we take any vector in row A, that means it's a multiple of the single vector that spans row A, so it would be of the form A, 0, -A. And if we take any vector in null A, it's going to be a linear combination of these two vectors. So it might be B times 1, 0, 1 plus C times 0, 1, 0, so it will look like this. And if I take U and dot it with V, I'm going to get, what was U? U was A, 0, -A. If I dot that with B, C, B, I'm going to get 0. I'm going to get AB minus AB, which is 0. So all the vectors in row A are perpendicular to the vectors in null A. We'll see that same thing is true in R2 with col A and null A transpose. So col A and null A transpose are subspaces of R2. Find a basis for col A. So what we do, come up here and look at B. The pivot columns of B, there's only one pivot column, and that's the first column. We take the columns of A that correspond to those pivot columns of B. So we're just going to take a single column of A, the column 1, 2. All right, and so col A is the space spanned by that single vector, so that's a line in R2. And you can picture that as this red line. And null A transpose, we want a basis for null A transpose, so I took A transpose, augmented with 0, and I got this matrix. So there's two variables, x2 is free, and x1 would be -2t. So a basis would be the single vector -2, 1. Geometrically, again, that's a line in R2. And you can picture that as this blue line here. This is null A transpose. And you can see if you take any vector in this space and dot it with any vector in the space spanned by -2, 1, you're going to get 0. So those are orthogonal subspaces of R2. And I believe that's the end of this section. There are some proofs that you can read if you're interested. And if not, you can just jump right into your homework and get that done.